First, I want to ask the round if there are news or new peoples that should be introduced. No reaction, so I would like to hand over to Omar.
Thanks,
Omar,
thanks, Andy.
yes.
Yeah, welcome everyone. So I wanted to take this opportunity to actually because Ube is flexible, so there we can make out of this one or what we want to make out of it. So I want to actually share a uh, broad-based picture on my experience with Bayesian statistics for the past 5 years as a water engineer, and apart from some generic themes on Bayesian statistics, of course, there would be discussion on some special techniques from the whole suite. But I would rather say it's a more broad uh, talk, and then the question answers may delve into something more specific. Um, so already I don't want to keep secrets what to expect from the talk. So I would first start with the historical timeline, give some context and recap of Bayesian probability. Then we can discuss again at some generic level how it was adapted by environmental scientists in general, maybe water science and engineers in particular. And then I have also prepared a small, I have uh, compiled a notebook. We can do a specific Bayesian inference exercise as well. But I think the historical timeline is generally, as engineers, we miss it, but that might be also something interesting to talk about, and we can have a discussion about that. How is something which on the face of it doesn't look should have anything to do with application, is more mathematical, philosophical. Why has it seeped deep into application? And that might be a good perspective. So starting there, so the origins of Bayes' theorem, as the name goes, the original idea came from Thomas Bayes. He was many things. Actually, he was a Presbyterian minister, wanted to talk about God, but he ended up thinking about a problem called inverse probability, and he thought how if you have evidence, how that evidence tells you something about the cause, the effect. If you only have the effect, what can you say about the causes that give that effect? So it was a very generic um, um, first attempt. He wrote something about it, and it was unpublished. As you can see, he died in 1761, and the essay that got published was in 1763. So posthumously published by his friend Richard Price. So that was where this idea of inverse probability more or less quantified in a way started, and it never gained a lot of attention. But then it was independently let's say partly rediscovered and formalized heavily by a more famous mathematician, Pierre-Simon Laplace, and then the current form that we see is due to Laplace. So that's Bayes' theorem written on it, written on the slide, that the probability of A conditional on B is the probability of B conditional on A times the probability of A divided by the probability of B. But again, as I said, before we go into more like the engineering side of Bayes' theorem, it's good to really also recap on the basis and interpretation of it. What is Bayesian probability, and how is it different from general probability? So probability theory has been there for centuries, 4 centuries of work. Everyone knew something about games of chance, and then how die throws happen, coin tosses happen. So there were bits and pieces of work here and there, and then Laplace did his work. But in the early 20th century, mathematicians wanted to formalize it, really see what are the bare minimum axioms and assumptions we have to make from which you can, uh, uh, derive all the theorems or identities of probability theory. So we will go through them, and then maybe the Bayesian interpretation comes. So probability theory divide of any interpretation can be just seen as a collection of three axioms. And those axioms are about a special mapping between two sets. So that mapping goes from F to P. The uh, three sets that we need to know is that the first set is called sample space. It is a set of all possible outcomes of our random experiment. So this is something we kind of might have heard, samples from maybe die through, and then it has six different members of the sample space. All the possible subsets of this sample space, or the power set of this sample space, is called the event space. So imagine distributing all the possible samples into small events, and then you have another set which is a special subset of real numbers from 0 to 1, which is P. Okay, three sets. What are the axioms? The axioms are that this mapping from set event space to P should always be that it should be greater than 0. There are no less than 0 members of the set P. The mapping for sigma, which is a sample set, should be 1. And then there is something called axiom of sigma additivity, that if there are two sets which do not, their intersection is null, they don't intersect with each other, the probability of the union should be equal to just the sum of individual probabilities. But coming now specifically as an example, let's say we have coin toss as the random experiment. It has two outcomes, heads or tails. I should use my pointer. Can you see my pointer? Can you see my mouse?
Yes, we
We
can
can
see
see
your
Okay,
your
good.
mouse.
So the coin toss has two possible outcomes. So that would make the sample space would be heads and tails. The event space would be basically everything, every subset you can think of from this set. So heads, tails, heads, tails, both together, and then null set. So generally for finite sample space, the power set would have 2 to the power n members, and then you just have to have correspondence to some number. So these were the bare minimum assumptions you make, and then things follow, like the probability should never be greater than 1 can be derived from these three theorems and three axioms. Many other properties can be derived. So far so good, but generally we start with probability theory defining a probability density. A valid probability density makes sure that it follows these three axioms already. So we never care about it. We say normal distribution, uniform distribution, or a Gumbel distribution, gamma distribution. But a valid distribution, sine wave cannot be a distribution, or some other any hyperbolic parabolic function with no limits cannot be a genuine distribution, because it violates these laws. So we generally start with accepted probability densities, but acceptance of probability density functions comes from these axioms. And if you know a probability density function, we know everything about there is to know about a random variable. So far, again, a recap, something into the basics, but Kolmogorow's axioms, probability is viewed as limit of relative frequency of an event. This is something we are more comfortable with. Coin toss, or things happening repeatedly, like maybe rainfall falling every year, and a die throw. However, it has been shown that if we want to talk about plausibility of a sentence, of a proposition, that did my house get robbed or not, which it's not amenable to repeated thinking. These are not frequent events. This is my belief about something. And if the belief follows a certain structure, and the structure is, you want to represent it by a scalar, it reflects common sense, which is again very precisely defined, and is consistent with Boolean algebra. For example, your belief also follows commutativity, that belief in A and B is the same thing as belief in B and A, those kind of properties. Then it was shown that these axioms this theory of belief is exactly the probability theory, and this is where uh, the the introduction, let's say, of Bayesian probability ends, is that somehow the fact that the mathematics that one should define for not knowing something or not knowing something precisely is isomorphic to the mathematics of frequencies. For me, I don't know why that should happen, but that's the case. This isomorphism is very useful, that you can define both things simultaneously, and that's the Bayesian interpretation of probability. You can talk in the language of probabilities for things which are not frequentist. Having said, yeah,
Sorry?
yeah, please.
What's isomorphic?
There is exact correspondence. You can derive back these axioms from these three statements. So that's Cox's theorem. What I say is true false logic under uncertainty is isomorphic. And isomorphism also has a very specific meaning in mathematics, which I wouldn't know because I'm not a mathematician. But that correspondence, they exactly have the correspondence. You assume these three, then you get back Kolmogorow's axiom, you assume Kolmogorow's axiom, you get them back. So here, when we were talking about, we don't have to think of this mapping as anything, neither frequencies nor beliefs. It's just, it says these are statements about sets. But somehow when you interpret them as frequencies, you kind of get consistency. That interpretation works pretty well for what you call probability theory. And if you say now P is my belief on something, it's also exactly the same thing. But given these three some cases, you can think of beliefs and uncertainty in other mathematical frameworks. Like there is fuzzy logic is a completely different interpretation. It's not Boolean algebra, in which it's not that a statement is true or false. It can simultaneously be a bit true, a bit false, that kind of thing. So there are other frameworks. But here, if you want to quantify uncertainty about your belief in according to a scalar, and then it should reflect common sense. One of the things of common sense is that the belief in A and B should be a function of belief in A given B and belief in B. So those kind of, let's say, technicalities, they somehow show that it's equivalent.
Okay.
Moving on from there, I wanted to accept that this again, this sounds like it's a philosophical debate. I wouldn't on the face of it think it should have anything to do with heavy practice. It's a very interesting debate. I think it's a very powerful pure science, pure mathematics debate. Why should an applied scientist care? This excerpt I would like to read from the book I'm currently reading is like, the scientific battle over Bayes' rule is less well known, but lasted longer than 150 years. So there was a lot of mudslinging around anyone who was using it, not using it. It was quite interesting what was happening, but it was not resolved until the dawn of 21st century. She doesn't even say 20th century. But I think better than the excerpt, I like the title of the book. It's a very long title and a very, let's say, provocative title. Theory That Would Not Die, How Bayes' Rule Cracked the Enigma Code, Hunted Down Russian Submarines, and Emerged Triumphant from 2 centuries of controversy. So very long title, and I mean, it's also very provocative, but there is truth to this title. So now, like, given we are talking about subjective beliefs here, why should it have a bearing on applied science? So coming there, I think this is what's interesting, and I wanted to draw just the schematic correspondence that we definitely are interested in the things in the bubble. That so Bayesian statistics is, of course, it's just a suite of useful techniques that stays, and like a tool, if you have a hammer, every problem is not a nail. It's when you have relevant problems you use, but it's also a language where you basically give probabilities to many things, not just frequentist things, and that makes those things in the bubble amenable. So we are after risk-based decision making. If everything is not certain, we are after adaptive planning. What if we messed up with the plan? We want to change as new evidence comes in. We as water scientists are engineers. do know, our models are not like Newtonian gravity or something. It's all messy things. It's a regression equation or something simplified. So how to make uncertainties explicit if we make decisions which would mean millions or billions of dollars spent. And then model selection, specifically just choosing a model and then assigning probabilities to them. Parameter inference, scientific hypothesis. So it's a useful suite of tools. So I think rather than directly delving into the statistics, which is then like, it's a specificity and why should someone care? I think the bubble is better. That the bubble doesn't exclusively get treated by Bayesian statistics. You can have different ways of doing similar things, but Bayesian statistics is definitely a very powerful place to look at if you are interested in something in the bubble. And I think as applied scientists, we are interested in that. So is it just a few people? Is it like, again, still a belief group, or it has been endorsed? Evidently, it has been endorsed a lot in water sciences and climate sciences in general, gaining a lot of popularity in publication, especially in my field of hydrology. There has been a lot of discussion. So already these are just papers to show that people have been discussing about it. And these are people discussing it. These are people who at the end are working on systems, catchments, urban systems, and decisions around climate change and rainfall, precipitation, droughts, etc. So in EAVAG, we already have Peter's group. Peter Reichhardt is one of the foremost, let's say, person who utilizes it and applies it. Peter has developed a lot at the intersection of environmental decision theory and Bayesian statistics. I learned a lot from Peter. So I would later on even put his book, I think, in the folder that might be useful. And still there are discussion going on why it should be useful for stakeholders, hydrologists, and how to deal uncertainty, how to quantify value of data, etc. Within our urban water management department, specifically the kind of work that we saw, you would see Jorg's and Andreas's name, one of the common names. So Jorg has been supervised and thought of many projects and was at the forefront of linking Peter's work and then our problems in urban water systems, from erroneous models to making more robust decisions. And then Andreas has been definitely a big force in advisory and for statistics. So there has been work on, let's say, I brought something up with combining expert knowledge and local data. So how to do it, Bayesian statistics would help. And then if you want to do something about flood predictions for ungauged urban basins, this would be something where you are not sure about certain things. You want to combine expert knowledge and data, whatever sparsely it's available. And I worked on, if you have alternate forms of data, can you update parameters? So specific examples of something more generic, but I did want to start from something generic. This only shows that Bayesian inference, Bayesian statistics is a tool, which it surely is. It is a tool, but it's also a language where we start talking more in terms of probabilities and things likely happening, not likely happening, and not giving very clear-cut answers where they don't exist. Now I think we go into the specifics of it, and it's just one of the specific renditions of it, because the Bayesian theory is much more generic, and it's used in computer science and spam filters and machine learning and everything. It doesn't belong to water science or engineers. We use it. So for any generic model that we are trying to model, and the system responds through a deterministic model, and then it has some error over and above it, and we say that if it's just an additive random error with certain structure, statistical structure, certain probability density, you say that, okay, the sum of this random error plus a deterministic model output should give you observations which are random. So that's kind of, you assume that that's generally how models are. And now the question is that the Bayesian question would be, given some observations, what is the value of parameters that generated them? What are the, and here the interpretation, all the discussion we had on, or all the talk that I had on interpretation comes into play. Parameters, they actually are constant values out there. We just don't know those values. Okay, some parameters are just made up, but still they are not stochastic per se. They are constant values, and we define a probability measure over them. We define probability. What are we doing exactly here? We can just keep doing it without giving it a thought, but we really are doing belief updating. That's like two different, something very practical, like a model trying to predict rainfall runoff, and then we are updating our beliefs in those parameter values given the observations, and that happens to Bayes' theorem. So this would be like, what we see here is like the rendition of the Bayes theorem. If you have some observations, concretely we can think of discharge in a drainage network or flood inundation, and this was our just swim model, deterministic model, and then we had assumed some error structure. We want to know this. So it's a reformulation of calibration, and now the question would be, why would we do it this way? Why don't just minimize some cost function? Then you get, one can do that, and that's a very useful method as well, fast nonetheless, but one doesn't know the uncertainty in parameters. Then it's equally likely the best guess parameters that you get by minimizing a cost function. There are other combinations of parameter values which also fit. And then if you want to do interpolation using your model and you're not sure about the parameters, and then in interpolation the parameter values really play a role, you might be uneasy. You rather would like the whole range of possible parameter values going in your model and then predicting something. To have that, to have ranges and probability defined with the parameter values, which actually are constants. Actually, there would be some quote unquote true parameter value for those models, which is a different debate. We won't go, but assuming there is that, we want to always work in ranges, and this is where Bayesian inference really comes into play. So this would be the posterior probability density. This is called the likelihood function. This gets defined on what structure you assume to your error. You might assume a simple normal distribution which is identical, then it's simplified. This is your prior belief, and this is a formal way of encoding expert knowledge. What you already know about the catchment or your system, or where you earlier think the parameters should lie, physical constraints, whatever. This was one of the most uneasy things about Bayesian inference generically also. Like, science sounds very objective, and there should not be subjectivity in it. And of course, if two people have different priors, their posteriors would be different, and that's totally fine with the theory. Suddenly we have a theory which allows for the same data reaching different conclusions if the priors are different. That feels wrong for what I as an engineer was taught for my bachelor's. But then you also see we do it when we want to calibrate models. We put physical constraints that in the optimizer that we use, the parameter should not go beyond certain ranges, and that can be done more formally through this. So the benefits, again, this is like a teaser. Of course, we can always go into the details. I would say some that I delineate is that it captures parametric and model structure uncertainty. And that's something that we would always need, where we always have a complex system. Environmental systems are out there. We don't do control experiments always, which can have precise equations. Our models swim or whatever. Even complex models would be inexact. So I think we would always need to also kind of know how sure we are, especially if we are really extrapolating. And then these, apart from the probability that we assign to parameters, which is the inverse problem, then the prediction is not just this deterministic prediction. We also get these intervals which Meteor-Schweiz gives us, and somehow coronavirus predictions don't have those intervals, but we get, and those probabilities then we can do risk-based decision making. If you have probabilities, you can use utility theory, etc. But you need to have probabilistic predictions over and above your deterministic model to say something about risk. So this is called this would be the posterior density. This is called the predictive density of your variable that you finally are after. And they basically capture everything in the statistical sense. They may not capture everything for us, because our problem may not be just predicting something as water engineers. They have multiple facets, but for statisticians, this is more or less all there is to know. Given some data, this captures all you know. This captures your updated information on how the system response will come in the future. And then something also very powerful is that it is amenable to sequential updating. So we have fair alt-off, we have collecting data one year after another, and then as longer time series of data comes in, Bayesian inference. So suddenly for first year, if I infer parameters of the model or infer something else, not just parameters, I can use the posterior as the prior for the next year and then add one more year of data and get updated posterior. I don't have to. So there are these nice things, and this is a good. It's a good thing to borrow as a language, I would say. It may not always be. Now to the limitations and how. So the limitations of at least Bayesian inference for models, because Bayesian statistics is broader than just models. You know, you can do those statistics. We can do it on data and many other things, and without having deterministic models in there. But of course, then you know, it's a problem for us, and it's a practical problem. There are computational costs, and there are, I would also say, for me as an engineer, there are conceptual costs. It's a lot of things to change of language, and maybe the focus, given finite resources of time, you have to make decisions. It's a lot to set up. So that is the case. Either people join forces and together we do calibration in the Bayesian paradigm and then have probabilistic outcomes and then school. But it is a cost. It may not be seen by those who really are just given to theory, but it's a very practical problem. So you always don't just predict once, you have to predict multiple. And what if you have your model solves Navier-Stokes equations and one run takes an hour? So, you know, so it is a constraint. It's not a replacement for proper mechanistic model building. And this is my, let's say, this is where I would say non-specialist statistician who are statisticians or some other field who have expertise in Bayesian theory don't help us or anyone else. They would rather put a simplistic model in place, which maybe does not represent the process, and then the focus could wrongfully go just to building a machinery called this Bayesian inference machinery, but that should not be the case. It's something that supplements the already existing exercise of building a more detailed physical model with an understanding of the system is necessary. You can't replace it. If the model is bad, no amount of statistics would help. It's just, you know, you have to kind of first make the model as good as possible and then model the deficits or the mismatches and uncertainty, the remainder through this mechanism, but not like we can't fit a line for a parabola. We kind of have to have the system understanding as well. Something that I looked into and I think that bothers me still is the meta uncertainty. Bayesian inference also works within the framework of assuming probabilistic models over and above the deterministic model. And the tricky uncertainty, which is the model structure uncertainty, is that we don't know how the mismatches will even come out to be. Even there's an assumption on what we think is the mismatch between your model output and the observations. And then there's a meta uncertainty, and then it's a cascading chain. Then you can do uncertainty analysis on your, there is something called imprecise probabilities. It's going on, and all the probabilities that you can give to, but it can become complicated. So one needs to know where kind of it's useful and it's very nice. For me, I think the most important use is it's the language of basically making things probabilistic, things which can't be made probabilistic in the frequentist paradigm. Then numerics, there are terms which also get used in the context of Bayesian inference, but they fit the same place in the Bayesian numerics as an optimizer fits in the position of, let's say, a problem for water engineers, and then they may not be fundamental. So one of those numerical tools that we need is a Markov chain Monte Carlo sampler, and it has the same position in this inference in the Bayesian framework as an optimizer has it. So it's one can maybe know the details of the optimizer, what it does. It's good to know a bit, but even if we don't understand everything about it, we can still use an optimizer to optimize. So what we see here, we are after parameters given some observations that is this distribution posterior, but there are some very heavy intractable integrals. You have to kind of integrate this out. This is called the evidence. And this doesn't change given a set of observations. This is a function of just observations because you basically you integrate out theta and psi. So this, if you exactly analytically want to calculate it, and there are very few cases where we can analytically compute this posterior distribution of parameters or calibrated parameters in the Bayesian framework. But what we can do is, instead of having an analytical equation, what we can do, we just can get samples from this distribution. And that's where Markov chain Monte Carlo equation sampling helps. So I would read this out. In Bayesian inference, we aim to compute the full posterior joint probability density. We face intractable integrals, and instead of finding the analytical posterior, we can simply sample from it. We can get samples which will serve the same function, because if you have enough samples of the posterior, then you run those samples through your deterministic model, and then you get the future predictions with the spaghetti. And that's what you're mainly after, because this is like maybe the stepping stone. And you can also calculate sample statistics through the samples. If I average out 1,000 samples, then I get the average of this parameter vector. If I get the standard deviation, so we get a lot. The cool thing about this sampling technique, Markov chain Monte Carlo sampler, is that you don't need this. It can only function with what's up here, a likelihood function and a prior. Multiplication is proportional to it. It doesn't need the normalizing factor in the denominator. A specific case of Markov chain Monte Carlo algorithm. So it's a chain. It basically is, let's say it's a particle jumping in your parameter space, and then it makes a chain, and it's Markovian because the jump always depends on where it is. So it's Markovian because of that. It's chain, and it's Monte Carlo because it's random. It's just jumping in the parameter space. So I don't know whether I should go into this algorithm, but Andreas has a package in, SIAMD works a lot on samplers as well, good efficient samplers which can explore the parameter space. And Andreas has a package in an adaptive MCMC, which is an adaptation of Metropolis Hastings algorithm. And then there are more parallelizable samplers where multiple particles jump, and then you can have parallelization. You can use parallelization there. So what we are after, if we don't want to go into algorithm, is we want to jump in this parameter space in a way that finally the samples follow this distribution. And there are proofs why jumping in this very funny way, which I will go through what this funny way is, converges to that distribution. Heavy proofs around it, but there is already proof that you jump in a certain funny way in the parameter space, and after a while, if you just see how probable was that particle in a certain region of parameters, it would be proportional to the actual density, the posterior density of parameter. So should I go through this? Maybe I should go through this. So so you have now you want to get samples from a distribution. It doesn't even have to be a posterior distribution, any distribution. You know, when we ask a Python or some language, give us samples from normal distribution, give us 100 samples. There's an underlying algorithm which kind of is able to generate from how does it, and we need to know that we actually have samples which follow a certain distribution. Univariate cases become easy, but what if it's a very complex multivariate case? So that's what sampling algorithms do. And here what we have to follow is basically we start somewhere in this multidimensional space called X, and then we jump from that place using some distribution Q, which is the jump distribution. It has nothing to do with posterior. And then this jump distribution proposes a new place to jump. It just says jump somewhere. Should the new particle be relocated to the new position is based on this acceptance probability. If the new place has if the evaluated probability there is follows this certain rule, then the particle is allowed to stay there. If it doesn't, then the particle stays where it was. It just proposes a new place to jump. And sometimes it jumps, sometimes it stays, and it keeps jumping. And after a while, these jumps, when you collect where the particle that was jumping was in this parameter space, that jumping of the particle exactly reflects the underlying distribution. It converges to the posterior, so we get samples. What else?
Sorry, Omar, this
Yeah.
criteria for the jump, is it to jump not too far, not too
So
close, or
the thing
can you
is,
paraphrase it?
the thing is, I would say that definitely, Andreas, Carlo would be better people to ask. But the thing is, the proof of convergence is for any jump distribution. Certain properties, any jump distribution will still converge to the underlying pi. That's the proof. Because it follows certain conditions, detail, balance, ergodicity, and then you see that it will first converge, and then the convergence will be the distribution. But for us, we want whether the convergence happens fast or not. And that's where your question comes into play. Depending on the jump distribution, your convergence to the actual distribution you are after would happen very fast by 1,000 samples or 10,000, or it will happen to this limiting case of infinity, which nobody has that much time. So I think it's really important to tweak that. The Siam does this course which Carlo explains the different jump distribution. Ideally, the jump distribution, if it has the same covariance structure as your underlying posterior, then it's the best case, but that's something we don't know. So I would say, yes, the jump distribution should be just more or less kind of, it should be, of course, comparable to the where you think your parameter posterior lies. If too big, extremely narrow would have weird effects, and then the convergence is slow. And then there are these diagnostics later. Once your samples come, you see whether it has converged or not. There are Gell-Mann's different statistics you can use. I use my eyes generally, but you can, you see whether the distribution converges. So the jump distribution has a very practical significance, and the adaptive algorithms that Andreas has, he has implemented the algorithm from Vihola, and the algorithm basically tweaks this jump distribution on go. It kind of first 1,000 runs, it tunes even the jump distribution, and then the next 1,000 it just does. I hope that answers your question. And now we will do an exercise. We will try to, what we can do is that we will use 90 years of annual maximum daily rainfall time series. So it's the annual maximum of the daily in a year. What was the maximum rainfall per day? And then if you have 90 years of the data from a model or actual observation, you want to fit a generalized extreme value distribution to it. It follows from theory, extreme value should follow GEV more or less. And then you want to fit this distribution. This would be our model. And then there are simple techniques already. You can use packages in Python or elsewhere. It just gives us the best fit values of these parameters. In our case, this would be the eta, sigma, xi parameters. We can 3 parameters, and or had it been a normal distribution to fit, we need mean and standard deviation. But now we are not just after the best case, best fit. We want to know, after these 90 samples, what are all the possible combinations of these parameters that could have produced it? And that's what basically this inference would maybe help us to do, is give a distribution, a kind of a scatter plot of these parameters. Let's see whether I can share this script. What can you see?
Jupyter Notebook.
Okay, good, thanks. Let's just run them. I import some modules, and then I import this time series, which looks like this, basically just timestamp, well, year, and then some values. So, and how does it look like as a time series? It looks like this: 80 years of data. This is kind of rainfall with some units. I would, if I have to take a guess, this should be in meters if it's a daily. Yeah, that should be my guess. Then if we just stack this up here and see the histogram, this is what more or less it looks like. And it kind of looks like this is the empirical GEV distribution. And now I just use the Python package, which is stats generalize extreme. I say fit using the data, and very easily it gives me the 3 parameter values. So for this, these 3 parameters, so it took us like 30 seconds, maybe less, to give us values. And it says this is the shape parameter location, and which is good, fine. But now I want to rather know the spread of these parameters. So I define a prior. It's a very simple prior in this case. All I say is that I do not allow the scale and the location parameter to be less than 0. If it's less than 0, I say that my prior belief is 0, and the log of that prior belief is infinity. And if it is not 0, then it's uniform, then it's like it's fine. So that's what, so we always use in log posterior and log likelihood, and then multiplications become additions, but things become more tractable when we are jumping and evaluating these. So this is my prior is like basically uniform, but it just excludes the negative space for 2 parameter values. Third one is allowed to be negative. Yeah, there's 1 parameter that's allowed to be negative. There might be a bug. I might be calling shape location, location shape, but I think that's beyond that doesn't have a bearing on the what we are trying to do. I will just figure it out whether I'm interchange the names of the parameters. Let's see whether it works, whether we can evaluate these probabilities. I give my initial guess of these 3 values as my prior guess, and it should tell me that according to my prior belief, these 3 values are forbidden. So it's like minus infinity because 2 of them are negative. So I do get A equal to minus infinity here. And log likelihood gets defined through generalized extreme value distribution itself, which we are assuming that our rainfall is following that distribution. We just don't know the parameters of it. But Bayesian statistics gets extended. You can assume different models, and then you can also get a probability on those different models. How probable is it generalized extreme value, and how probable is it normal? And given its generalized extreme value, then how probable are these parameter values? So you can cascade it. And then this here encodes the Metropolis Hastings algorithm. It's an adaptation from, I found it already implemented by this person, and then I adapted it for our case a bit, just here and there. So Andy, to your question, the jump distribution I just write here, and I just say make it normal and then make it jump with this standard deviation. I just chose it, and this can be, so this is a very inefficient algorithm from my stand. It's like, but it's transparent. You don't load a module from Python. More sophisticated algorithms exist, like MC. It's a very nice name by some astronomers. They put MC Hammer, and that's a ensemble Markov chain, ensemble sampler, and you can use parallelization. So then this encodes the sampling method, and it has the same importance as an optimizer. It's more computationally expensive because optimizers' philosophy is be smart and go towards the minima or the maxima. You don't want to know what's happening to the space, but samplers want to explore the whole space. So you need more runs already to quote unquote calibrate your model. And then you definitely need much more runs to predict, because you are not now allowed to just predict using fixed parameter values. You then run all of those parameter values through your model. So it basically becomes a heavy exercise. Useful for many cases, many times it might be an overkill, and that's something that we have to decide.
I'm interrupting as a moderator. It's 2:20.
Okay, so I just 2 more runs. Then this is now running. If you can see, it's 15,000 runs. It's calculating the posterior, and then we will have it in some time. Yeah, it should not take much time, maybe another 5 seconds, and then we can see what we have. Actually, we already see what we have from my previous run, so I can show you here. So now we have the same parameters, but apart from this best guess for shape, location, we have spread and we have dependence with each other. And this in turn now can be used to quantify more uncertainty than just the frequentist uncertainty or rainfall. So rainfall is a frequentist event, but the parameter of its distribution is not frequentist. We just don't know what it is. And if instead of 90 years, I get 290 years of data, this spread will shrink. We will know more clearly what is the parameter. If given the assumption, the parameter, it's a stationary distribution, all those assumptions. But that's something that, that's why the Bayesian interpretation is there, that we are quantifying our beliefs. So then we have the spread, and then this can be used. And if I see that it should not be that different, these values should not be that different than what Python already gave us, these are the mean of the posterior, it's exactly as the best guess that we got from the early on from the Python module. But then we also have spread now. And this is a simple case, but you can use it for more complex cases where you actually don't have rainfall, but you are trying to model some phenomenon related to water science. The model is a bit imperfect. You don't have long time series of data, so you can't exactly identify the parameters, but you want to do scenario analysis, and it's important that your conclusions heavily depend on your parameter values that you get. So you don't want to just use your best guess. You want to explore really what's the bearing of your conclusions based on the whole parameter space. And then this way of thinking becomes useful. And with that, I would say I end my presentation and we can have a discussion.
Cool, thank you very much. Are there any questions from the audience directly?
Well, I have not really a question, but I just wanted to say something. You know, when you said before that the Bayesian method is kind of subjective, so that from the same data you can get different results, and that's not really what we got taught, you know, as scientists, whatever. I beg to differ, because I think like all these models, anytime you model something, it's always subjective, because if you choose a regression, it's on you to choose whether, like you said before, you use a straight line or whether you use, like, I don't know, a sine wave or whatever. So it's always some subjective method, or whether you use SWIM, which uses some physically based models, or whether you use statistics or whatever. It's always just our best guess on how things are.
True, I agree. And I think it was just like that's what the debate was. And finally, the acceptance came that, I mean, almost never in the history of science have we never have to deal with uncertainty. So this idealization where, you know, there would be some fine day, we will have all the data and the model fits perfectly, and then we don't want subjectivity, might work in some cases, but in some rough cases, as you said, where, you know, models are just approximations to fit some data and data is not sure, we do make many subjective choices. And it's a Bayesian framework gives an operationalizable way. And one of according to another interpretation, Definity's interpretation is that it's a rational way of kind of updating. Otherwise, you would be turned into, let's say, a money source, or like saying someone can, you know, make a lot of money out of you, where you always lose if you don't maintain and update your beliefs according to these rules. So I agree that there is that subjectivity, and then Bayesian inference allows that encoding. Like priors, I would say that you can, without, it is still not clear, you know, Bayesians have not also figured out how to really elicit priors, and there are many loopholes still in it. But it's good still that if we know for sure that there is some agreement by some scientists on certain parameter values, there are these lookup tables and ranges, and then that can be our priors without getting to, maybe, let's say, without dealing into the philosophical implication, but that we do use them. I agree with you that there are these lookup tables, and then we use parameter ranges. We might as well just formalize them and put them as priors. So, fine.
Okay. Well, thanks for the presentation.
Thank you.
Maybe connected to this, you introduced, or you just quickly mentioned that you could do it iteratively, assuming the model and then calculate the parameters. And you could use different models for the same purpose in the end, and then you could compare these models and then also compare their performance.
Yeah.
Do you have something like in mind when you talked about that, or how would you in the end compare the different assumptions? And
Yeah.
I think it's quite difficult. It's
Yeah.
more judgment by the modeler than anything else, right?
True. I would say that's why, first, I think it can be done within the Bayesian framework. But again, it's really, you have to take control of what you're saying with these metrics, Bayesian metrics, by model comparison, or and it's okay sometimes to just contradict, or like, hey, this got messy and it doesn't make sense, or I just say what I see. So, but it's a formal way of comparing. You give probabilities, or you do Bayesian model averaging, and so that those metrics stay. Like early on, we used to do these more frequent is hypothesis testing of statistics, where we have null hypothesis, or the H1, the other hypothesis. You can now have these multiple models if you are trying to have the same data, and then you create a Bayesian metric, say what's more likely. But you might as well have a different metric. I don't know. There are these metrics which penalize a more highly parametered values, or some metrics say if it's physically based. So I think us as engineers can never be in the back seat, and then this probability would not make the decision for us. I mean, and but it does help to, if you really have just two competing hypotheses, and you can really get which is more likely than the other. We can anyway see it one way, as one very engineering way of doing it is like, this model makes more errors, this makes less errors, better fit, better model, something like that. But if you want to flip the language to language of probabilities, say how likely is this model is the true model till more 1 year of data comes in, then this method helps. But it doesn't counter one's intuition. We would anyways reach similar conclusions based on Nash-Sutcliffe efficiency or something, but you won't be able to talk in the language of probabilities. I think that's and the sequential updating actually very cool. I would say that is like, that doesn't exist with these simple least square metrics and all that. Sometimes if you calibrate the model using 1 year, another year, and then you calibrate using 2 years together, these least square metrics, or some metrics that we just make up which are useful, would not lead to the same parameter value. But Bayesian updating is consistent in that sense. It's, let's say, one of the nice things about it, that if you update using 1 year, then you update using second year, you will reach the same parameter values if you update it with both years. They exactly, so the updating is consistent. That's it.
Okay, thank you. Unfortunately, time is already almost
Omar,
up. Is there a last question?
I would like to ask you one question, Omar. Thank you for the presentation. I think you managed to explain and outline why this is useful, but still it remains a challenging task to pursue this approach. How do you think can we translate this so that it's been picked up by practice people?
I think I asked I mean, I share your skepticism, Frank, as well. I think as practice, we do not have maybe time, 2 years to ponder over nicely. So that I have discussed with people who actually are heavily working on the statistics of it and not just, and they say it's at the end, it's not that difficult because it's like we have the swim, would be additional buttons in the swim, which will do it for us. We would also start maybe teaching already from more probability theory already to our students as engineers early on, but the heavy part would be done already by the software. So this operational, it becomes very operational. If the theory is very like, theory is cumbersome, you know, I am very slow and then I do it and it takes me a long time. But once we see actually it is useful, it would start becoming part of packages. And that's why the resurgence of these techniques, especially by computer scientists, is what really now makes it the belief. It's the same belief that we lend to it because we lend the belief to machine learning. So it is useful, you know, spam filters and many updating mechanisms have very practical applications. But also, like machine learning, I don't like mystery around it. It is only as good as the modeling exercise, what the modeling exercise and data will allow you to do. It won't solve world problems. It's what your model, what you expect have a good model will allow us to do. That's what Bayesian inference with maybe talking in the language of probabilities will allow us to do. It's kind, but it's, you know, at the end we have to also always think and not just take things for face value.
So machine learning as a door opener for Bayesian statistics. Not really.
I just wanted to now on the lighter note, and I would kind of end. It was very tantalizing to rather name this presentation an introduction to BS, but I did not. So
that's a very nice ending of this presentation. Thank you, Omar.
thank you very much. I would appreciate feedback by someone later on if someone has any things I can improve, but not now. Maybe just drop me an email, please, if you have something.
Yes, I have 2 points to add. When Guy is presenting next Monday, please tune in. And also the labeling exercise for the UVO data is still going on. If you have questions regarding that, please let me know. Otherwise, I would be glad if I hear from you until this Friday. That's it. Thanks for joining. Have a nice day.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye.